On January 26, 1926, John Logie Baird, an engineer from Scotland, successfully demonstrated the first working television system using mechanical picture scanning with electronic amplification at the transmitter and at the receiver. Remarkably, it could be sent by radio or over ordinary telephone lines. A mere 2 years later came the first transatlantic transmission of television from London to New York. 30 years later, also in Scotland, an obstetrician called Ian Donald teamed up with an engineer, Tom Brown, to create the world's first ultrasound machine. He hoped that someday every pregnant woman would have at least one scan. How times have changed. Innovation throughout history has always been about breaking boundaries. Can we make things more affordable, portable, practical, scalable? In short, can we do things better? What John Logie Baird and Ian Donald had in common, apart from being Scottish, is that they revolutionized the transmission and processing of signals. Despite our progress since then, we at the SAMPL Lab believe that we are only at the beginning of what can be achieved in the field of signal processing, that medical imaging devices can have even higher resolution, that communication systems can be faster, have a greater bandwidth, and that we can harness AI and big data to process the enormous quantity of signals information around us in a smarter, more efficient way. Here are some examples of what can be accomplished.
Bobcat 1-2.
In today's world, we use signals with wider and wider bandwidth. We want to communicate more information. We want to see better with better resolution.
Everything in our life is signals. It's around us. It's in ultrasound, it's in MRI to get a better picture, it's in radars.
Signal acquisition and processing is limited by the sampling rate. The traditional minimum sampling rate that is required to enable the signal's accurate reconstruction was determined by two electrical engineers, Harry Nyquist and Claude Shannon, and is called the Nyquist rate. Claude Shannon laid the foundations for information theory, which enables the electronic communication networks that now lace the Earth. The Nyquist rate was the first boundary defeated by the SAMPL Lab, a revolutionary, multidisciplinary lab at the Weizmann Institute of Science.
We could think of the kids' game of connecting the dots, where you're given a bunch of dots, and if these dots are close enough to each other, then you can easily trace a line and a clear image pops up. The Nyquist principle is basically dictating to us how close we need to make these dots so that the true underlying signal could be revealed. What we're working on in the lab is how essentially we can make these dots further apart, because that allows us to represent signals using less resources,
less energy, less size, more cost efficient.
So it's really a combination of looking at these systems end to end, designing them together, using models and everything we know about the system in order to be able to extract information beyond the bounds that are dictated by physics.
It's like a playground. We generate here between 4 to 6 prototypes a year. This is one of a few labs that literally doing that.
Our lab is an eclectic thing in the Weizmann sphere. We have electrical engineers, physicists, computer scientists, and me myself, I'm a medical doctor, which is far from engineering as can be.
We work on a variety of different signals, communications, radar, homeland security on the one hand, optical imaging, biological imaging, and today a large part of the lab is devoted to medical applications that we're really enthusiastic about.
We really want to make sure that we're working on true unmet needs so that we can bring real value. In order to do that, we maintain close collaboration with both the industry and the medical community. Every 3 to 4 months, we host here a unique clinical forum. This clinical forum is an infrastructure for collaboration, for brainstorming, for forming new research projects.
We've been looking at super resolution ultrasound, where the idea is that we can inject microbubbles into the bloodstream and then use sophisticated machine learning algorithms to actually track those bubbles, and in that way we could see tiny blood vessels that we couldn't see before.
By using these methods, we could have a viable way of characterizing breast tumors better. And apart from super resolution, we work in order to improve clinical diagnosis in other methods as well. We work to improve the hardware of the ultrasound device itself with the goal of making a high quality, portable, small ultrasound device which could also be worn as a patch over the patient's body, enabling continuous monitoring.
In communication, what we have is basically a joint radar comb. So if I'm a target, basically the signal is coming through me and going to the other radar without the need of any communication device. This is called a joint radar in communication.
This is very important, for example, in autonomous vehicles, where we want to be able to both sense the environment, but also to communicate our findings with nearby vehicles. So in the lab, we've been working on interesting new materials and new antenna devices that will enable us to communicate at higher and higher rates, will enable us to communicate at further distances to accommodate more users in a more secure fashion.
Today we can do stuff that we've not even dreamt 5 or 10 years ago.
We'd like to break some more boundaries, to use what we've discovered to impact scientific discovery, to improve health, and to benefit society.
Make clinical diagnosis more robust, more precise, improve human lives.
Join us in our journey from theory to practice.